Okay, well, thank you very much. Thanks for the invitation and the introduction, Robert, and all the other organizers. So yes, what I'm going to be talking about today has, in a sense, little to do directly with quantum computation. It's really about classification of topological phases of matter. And well, you'll see there's various things you can classify. So I'll classify one of the possible things. And it's related to pumping charge, but not necessarily. And it's related to symmetry. So this is joint work with Roeck and Jappens at the University of Leuven and Fraas at UC Davis. So I will talk first about Thouless pumps, as Robert announced, although it was not in my title, and quantization of charge transport. Then I'll say a few words about the general setting of the talk, which is quantum spin chain in the infinite volume limit. And then I'll talk about really what I want to classify, namely loops of a particular class of states, namely invertible states that are invariant under symmetry. And then I'll talk a bit about, what do we mean by classifying these loops, and that has to do with a certain notion of homotopy of states. The framework, well, I have the word algebras in it, so I think I fit here. I have symmetries and algebras, so I think that fits the talk. So it's I'll use the operator algebraic framework, although I'll try to minimize a little bit the technical aspects here to be able to explain something. But the important thing is everything I will say is on an infinite spin chain. So very briefly, since I'm talking about, it's a generalization of old stuff. Old stuff is the work of Thouless in the 80s, who first realized that you had quantization of charge transport in some situation. So here's the situation. He considers, in fact, what Thouless considers is really a periodic, one electron in a periodic potential. Okay, and the potential is periodic both in space and time. In his case, in fact, we don't need spatial periodicity at all. But you have a Hamiltonian, which depends on time through the potential. So you really think of that, the black potential here, slowly moving from the left to the right. Okay. And so that's the Hamiltonian. It's a very simple situation. And what Thouless shows is if you make this change of the potential slow, so you are in the adiabatic situation, and you are such that the Fermi level remains in a spectral gap throughout the whole process, right? So, I represent here by these wells being filled up to some point by particles. It's a bit of a semi-classical picture if you want. Then if I move that slowly and I go through one whole cycle, what happens? Well, I have the content of one of these wells has been moved by one site. So I've done a cyclic transformation. The end situation is the same as the initial situation, right? But something has happened in the meantime, namely in fact, an integer amount of charge has been moved. One way to think about this is, and there's two ways to think about this, and I will use only one in the following. You can think, well, there is a reservoir on the left, and charge has been pumped out of that reservoir to a reservoir on the right, okay? Now, you see, this is always a problem because you transfer a finite amount of charge from an infinitely large reservoir. So one better way to think about this is you sit here across a line, you pick a random line, just look in front of you and count the number of charges that pass in front of you. Okay, that's the better way to think about this and to measure that charge transport. What we will do instead of having a reservoir, that was Thouless' situation, we'll think the reservoir is just the infinite chain on the left. It's also a good reservoir of charge. Okay. So it's, things are quantized. So I will not go into this in detail. It's non-interacting fermions right here. So really everything all you need to know is about the family of Fermi projections. Okay. So,
comment.
Yeah.
Do we record?
The record? Oh, yeah. Okay. So I shouldn't say too many silly things then. Okay. So, okay. The point of this slide is to say there's a topological picture that underlies this situation, right? In fact, there's various ways of phrasing it. I think this is the most general one where You don't require spatial periodicity, which was Thouless' situation, right? All you need is you need to, this equation here, the eigenvalue equation, as a differential equation, has solutions for all complex energies, right? And you look at those solutions that are, let's say, integrable at 1 infinities. That gives you a family of, depending on E, that gives you a family of states. Okay. So if I plot these family here, right, I'm here at t equals 0. That's, you see here, I have the t axis, right? So I have here t equals 0. The spectrum might have gaps. So here are the in purple. If you can see that the colors, that's parts of the spectrum, and the Fermi energy is here in a spectral gap. Okay. So the Fermi projection would be the projection here, and this is a function as time here changes, the spectrum changes, right? But one thing is important: the Fermi energy here remains in a gap throughout the system. So the Fermi projection is a well-defined object throughout. And it's basically I have a loop of Fermi projections, right? Because what is here changes, but at the end up here at t equal capital T after 1 cycle, I'm back to myself. So I have a loop of Fermi projections. And eventually what I can do is I can think of the whole thing. I can have a nice topological picture where I have a fiber bundle, and I can understand the charge transport as some Chern number of that part, the topological quantity, which explains why it's changed. So what I want to do is, really what you should remember from this is there's this loop of Fermi projections, right? So I start with a Fermi projection, then I make some transformation, so the Fermi projection changes, and at the end of the day, I'm back to myself. Okay? And that was a non-interacting situation. So now if I have some interactions between my electrons, so I'm on a chain of interacting fermions or quantum spin chain, then I want to find the same picture again, but of course I don't have a Fermi projection anymore. So here is the setting. So now the setting I really want to be working on is a quantum spin chain. So for me, a quantum spin chain is just an infinite tensor product of, it could be 2 by 2 matrices, so it's just qubits along a line. Okay. So I call the algebra of observables, hey, it's just this infinite tensor product of matrix algebras. Okay. 2 by 2 matrices, if you like. A state, and that's maybe the only thing that is a little bit surprising or unusual for you, rather. I will think of a state not as a vector in a Hilbert space, but as a linear functional over the algebra. So it takes an observable in the algebra and gives me a number, which is the expectation value of that observable. Okay, so it's taking the sandwich in a vector state. So, but that. Right, so my states, when I don't say anything special, my states are only linear functionals. They're not vectors in a Hilbert space. This plays an important role here. Okay, so I want to insist on this. So I will have an algebra of observable, a state or family of states, and then there's a symmetry. So a symmetry, what is it? Well, it's a transformation of the algebra of observables. Okay, so I have a group. This will always be a compact group. So either it's a finite group, Zn, or SO3, or SUN, whichever one of these compact groups. And it just acts on the algebra on site, right? So it's important. This is an on-site action, it's a very local action at each site. So really on site, at each site, this will be really a conjugation by unitaries. You can have a unitary representation. Yes?
The action on each side the same?
Yes, although it will not play. So where will it play a role? No, it will. It just plays a role because really what we classify is fundamentally what plays a role is the action, not the group itself. So it's really this action which will play a fundamental role at the end. So it is the same at each site. And when I say it's an action of a group, it satisfies this. You know that from representation theory, right? The action associated to G in H is the action of GH. So my group, you see, is multiplicative in notation. All right. Now, of course, if I have an action at each site, well, it extends to an action on the whole chain, and I will use the same word, the same letter. Good. Okay. So, what states will I classify? And what sort of state? So first of all, I want it, for now, what I have is an action of a group. If I want that to be an actual symmetry of the system, then the state has to be invariant under that action. Right? So that's what I say. Psi is G-invariant. That means if I take an observable, rotate it, right? Let's think of the group as a rotation, rotate it, and then take the expectation value. It's the same as before rotation. So the state is invariant under the action of the group. Okay? For all element G, of course. Please stop me, right, if some of these notations in particular are a little bit unusual. Here. Now, really the key assumption here is we don't have non-interacting fermions, so we really want to have an interacting system, but not an arbitrary interacting system. So our assumption of the state is this notion of invertibility, which I think goes back to Kitaev. And it says the following thing. It's always a little bit surprising, but I'm sure most of you have seen a version of that. So my state is invertible. What does that mean? That means I have a state on the chain, and I can find another state on another chain, right? I can stack a second chain on top of it with another state on top of it, right? Such that the product of these two things can be deformed to a trivial state, namely a product state, okay? My notation here, this equivalence relation is this deformation. What does this deformation mean? It will play an important role. So, two states are equivalent if I can get one from the other by Hamiltonian evolution, right? With a time-dependent Hamiltonian, right? So really what is important here is that this Hamiltonian, I don't write the details, but this Hamiltonian is a sum of local terms. You can think of finite range, or really long range, but then you have to have a decay of the interaction strength faster than any polynomial. Okay? So that's this notion of equivalence, right? I can, if I was in a finite spin chain, it would be local unitary equivalence. Here, in this infinite setting, then notations are maybe a little bit more complicated. Okay, so that's, I will consider only these invertible states, and what should you think about? Invertible states, that means short range entanglement. There's no long range entanglement because I can get rid of the entanglement and come back to a product state by acting only with a local Hamiltonian on the state. Okay? One way of thinking of short range, or phrasing what you mean by short range entanglement. Yes? No, so I don't make any assumption on a gap at all. No, but okay, so it's a family of Hamiltonians. And the rate of decay of the interaction terms is exponential. Think of exponential. You can do a little bit better, but that's the only assumption we have on the graph. You see, if you had a family of gapped Hamiltonians, and you were to look at the family of gapped ground states of that Hamiltonian, then you could construct such that would be the adiabatic evolution that would map you from one ground state to the other ground state, right? But then what would show up here would not be the Hamiltonian itself. It would be the generator of parallel transport, the quasi-adiabatic evolution. Okay, so that's it. So I will always talk about invertible states. And the final thing is, so when I say a G-invertible state, what does that mean? It's a state which is invertible. It's G-invariant, and you can invert it using a G-invariant Hamiltonian, right? So it's invertible, it's G-invariant, and so along the path, the Hamiltonian itself, all Hamiltonian terms, all the interaction terms are themselves invariant under the group action. Yes?
What about this other state? When you introduced invertibility, there was another state beside R. Does it also have to be G-invariant?
Well, so you see, I don't need to. No. So this is G-invariant. Everything is G-invariant, right? Along the path, all the things I will talk about are G-invariant. Okay. So you might have seen that setting already, and you can classify these states. Right? This is one way of describing symmetry-protected topological order. There's other ways, right? But in 1D, I think they're all equivalent. This is one way, and this is an old question, I think, which was answered first by Chen-Gun Wen in 2011 in the framework of matrix product states in one dimension. There's been recent, more mathematical work by Ogata and Kapustin and his group, who did this somehow in the full generality. These two works are closer in their setting to what I'm talking about here. And they said, okay, they proved that you can classify these states, these G-invariant states, and that the equivalence classes are labeled by projective representations of the group. Okay, that's not what I will be doing here. Now let's go back to my first slide. What did we have? We had a loop of Fermi projections, right? So here, this is also what I want to do. Now I take not states, but loops of these states, right? So you can think of as slow time evolutions of these states, adiabatic evolutions of these states. Okay. And now I want to ask the same question. So what are the equivalence classes of such loops? I still have to say exactly what I mean by, when loops are equivalent, but that's what I want to kind of classify these loops of states. So we'll have a one parameter family of G-invariant states, G-invertible states, right? And it's a loop because psi at s equals 0 is psi at s equals 1. Okay, so little picture, if you have the manifold of G-invertible states here, I will try to look at such loops and try to classify those. Okay, so you see, of course, if you classify those loops, you also need to classify the starting points of the loop. So, these two questions are, of course, related in the sense this is part of the general classification of the loops. Okay, because if you, is the question clear? Yeah. No, Robert seems skeptical.
No, I just this thing of the base point matters.
Yes.
Probably we're preparing for something that you will explain later. I mean that.
Yes, but you see, you can think that if I have two base points which are not equivalent, so I cannot deform one into the other, right? Mm-hmm. How would I then be able to deform one loop based on this base point into another loop based on the same base, on a different non-equivalent base point? Right. So what I will do is, in fact, what I will classify are the loops with the same base point, and then say, well, if I have a different base point, I can first deform the base point into. If I have two base points in the same equivalence class here, I can first deform one base point into the other, do the loop, and come back, and that's another bigger loop.
So sorry, I don't want to hold you off.
No, go ahead.
But I remember, so there's this old Mermin paper about topological classification of defects.
Yeah.
It's called a media.
Yep.
And there is a difference there when you compare loops when you classify loops with base points and loops without base points. And so the loops with base points, they will correspond to elements in the homotopy.
Yeah.
And without the base point, they will correspond to the Julicy part.
Right. So you see, I think it depends. It's a general question in mathematics whether, if you talk about homotopy, whether the homotopy will depend on the base point or not. Sometimes it does, sometimes it doesn't. So a priori, we don't know. Yeah. But since we know that base points already come in different classes, what I'm trying to say is it's not surprising that at the end of the day, the classification of the loops will also, in the first place, depend on the base points. Mm-hmm. But it's not, it's not clear that a priori that this won't happen. Mm-hmm. Okay, so the first question is, I wave my hands. I know I always move my hands a lot when I give a talk. So, but okay, what is a loop of states, right? If you think, when you define a loop, well, it's a continuous family of something, right? So here, if you think about it, so I need to have a notion of continuity on these states. Okay, and if you think about all possible notions of continuity on states, you realize there's nothing really that fits the physical picture by only invoking states. So what you always do is come back to, it's always the same idea. Here we're thinking about, we don't want to change long-range entanglement. So a loop for me is always going to be like this. It's something which is generated by a Hamiltonian, time-dependent Hamiltonian, but a Hamiltonian nonetheless. So my loops are always going to be of this form. The loop at S So the state at S is given by the state of 0 evolved with a time-dependent Hamiltonian, which I will call here. Okay. So again, if you like to have this picture in mind, think always of all these loops are adiabatic evolutions of loops. Although, again, there's no need of a gap going through that, right? But it's all everything when I have a time dependence or parameter dependence, it's always because I've evolved with a local Hamiltonian. Okay. And okay, if I have again, so now I have these loops, I want to, so what does that mean to have a loop which is G-invariant? Well, the base point is G-invariant, and the Hamiltonian evolving and generating it is also G-invariant. So I have this property all the time. So what is now, when I want to classify these things, what is an equivalence? Well, it's a deformation of these loops. How I deform these loops? By deforming their generators. So here's the picture. If I have here, here I don't. So here's a path. It doesn't necessarily need to be a loop, right? It starts here at 0, at s equals 0. It finishes at s equals 1 there. If it were a loop, this point would be the same as this one. Right? And then what do? I deform this path to the path at what I call the parameter here is lambda from 0 to 1. So it's another path. And along these lines here, again, it's again a Hamiltonian evolution. Okay, so that's my notion of a loop of states, a deformation of loops. Okay, all is always by deforming Hamiltonian space. And why? Because that's the right notion of locality that we want to see through this. Okay, so now, so we will see the idea of how to classify this is very simple, and it goes back to this picture of Thouless. So let's go back. So I have this infinite, now it's an infinite chain, right, of qubits, so whatever you want. And so, I said already one way to think about transports is to look what the current that passes in front of me. Well, we'll do a slight variation of this. It's more of an edge picture where I will say, look, instead of evolving my system through on the whole chain, I cut the Hamiltonian. So I have the whole chain, but the evolution, the Hamiltonian, I only take those terms which are on the left half infinite chain. Okay. So if something is, if something comes from that half infinite chain or that reservoir, but I've cut the Hamiltonian evolution here, things cannot go through. So if anything is transported out here, from minus infinity to it, it will somehow accumulate close to the cut. Okay. If it was electric charge will accumulate here. So I will think of that as being the G charge that accumulates here. I don't know what the G charge is yet, but the right notion of charge will accumulate here. Okay. And so really what I want to think of is I have these, what I call the pump state, psi minus. It's this, the base point evolved with the truncated Hamiltonian on the left hand. Okay. So while if I evolve with a full Hamiltonian, I get back at s equals 1, so I have a loop. If I evolve only with the half chain Hamiltonian, this is not a loop anymore, right? So there's no reason why this psi minus now at s equals 1, so the end of the evolution is the same as the initial one. In fact, precisely, it will in general differ by something which is here close to the cut. Okay, so we'll carry this G chart, and the important thing is, how did this G chart accumulate here? Well, it was pumped from minus infinity, or from that reservoir, right? But now that it is there, I cannot remove it locally because charge is a symmetry, so I cannot remove it locally from there, right? So somehow it will be stuck there, and I can do all sorts of local transformations close to the cut, but I cannot remove the charge from that point, okay? Locally. I could bring it there by, acting on the whole half infinite chain, but not locally. So let's think now a little bit about that pumped charge, pumped state. So what do I have? I know that I have short range entanglements, right? And I know that the Hamiltonian generating this is a sum of local terms. So it doesn't create long range entanglement, okay? And I know that the state at 1, not the pump state, but the full state at 1 is, I go back the state at 0. So what do I know? So you see, this pumped state, I obtain it by acting with the Hamiltonian on the half infinite chain. So if I'm far out there, where I act with the Hamiltonian, there's no long range entanglement. So far out on the right, the state doesn't see that there was a cut here and doesn't see the right half chain. So the state far out on the left is the same as the state at 1, which would be the same as the initial state, right? So far on the right, that's clear. Far on the left, for you, the opposite, far on the left, it's clear. Far on the right, nothing happens. I don't change anything there again because of short-range entanglement. I stay in the initial state. So that means the pump state differs from the initial state only close to the cut. Okay, that's this statement here. Okay, so these two states, the pump state and the initial state, are equal at infinity. That's one way of thinking about it, or they just differ close to the cut. Now, there's a consequence to that, which is, the mathematical consequence of that is what's called unitary equivalence of the state. So let me say a few words about this algebraic setting of these infinite spin chains. So some of you might have heard these words already. I don't know, the GNS representation. So here's what so I have this algebra, right, of observables on the infinite chain. I have a state here, I will apply this to different states. So let's think of a state omega, which is just a linear functional that takes observables and gives me their expectation values. So what I can always construct, and this carries the name GNS representation, I can always construct a Hilbert space associated to the state, a representation of the algebra on that as bounded operators on that Hilbert space. You see, so far there was no Hilbert space, right? There's just the algebra. So I can construct a Hilbert space, a projection, representation, and then I can find one vector in that Hilbert space, sometimes called the vacuum vector, such that what? Such that, well, this abstract expectation value, right? So it's I evaluate the linear functional on an observable, that's a number. I can actually compute it as I would always do in quantum mechanics, namely, I take my observable, I represent it as a bounded operator on the Hilbert space, and I take expectation value now in the good old sense with vectors, with that particular one vector. So that vector, we obviously call it the vector representative of the linear functional in that Hilbert space. Okay. Now the point is, if you have different states might not live in the same Hilbert space. So that's the point of these in these infinite spin systems. That's why you don't start with the Hilbert space, you start with the algebra, because there's one algebra, but there's different Hilbert spaces on which you can represent the state. This plays an important role. These are the physically, thermodynamically different states. If two states are really different at infinity, then you cannot represent them in the same Hilbert space. If they are equal at infinity, as we had, then in fact you can represent them in the Hilbert space. It's a little theorem. And so we are in that setting, right? The pump state and the initial state, they are equal at infinity. So I will be able to represent them both in the same Hilbert space. That's important. So I will be able to find a vector that I call, so I'll be able to find a vector associated to the pump state in the GNS Hilbert space of the initial state. And then, then it's easy to compare them. They are in the same Hilbert space. I'm in business. If you're a little bit confused by this notion, think about, let's say, fermions in the infinite volume limit, right? You represent, so if you're in vacuum, you represent, you can put fermions, you look at Fock space, right? And you can add an arbitrary large number of fermions, right? So in Fock space, there's an arbitrary large number of fermions, but there's not an infinite, the density is 0. In Fock space, any state in Fock space has 0 density, right? So you see there that you cannot represent in that Fock space, you cannot represent the state with finite density in the infinite volume limit. You would need to build another Hilbert space to do that. So it's the same situation here. Two states fundamentally differ from each other, namely they don't differ only locally, but globally. Then you have to represent them in two different Hilbert spaces. So the cut, I can find a vector in the Hilbert space associated with the initial state, which I call this, just change the point here. That's the vector state in the GNS Hilbert space of the origin. And the point is really, why is this important? Because by doing this, I'm back somehow in a zero-dimensional situation. I don't have this spin chain really anymore. It's just one Hilbert space. Everything is there, and I just need to compare two vectors. I need to compare two vectors. They're both G-invariant. By abstract nonsense, in this GNS Hilbert space, there's always a unitary representation of my symmetry. And this is what I have here. So that the symmetry is, as you know, it's just, there's a unitary action. You get this. And I have two states. One, which is the base point, right? You can always choose, you can always arrange for this to leave the state exactly, the vector exactly invariant. So there's no phase here. The pump state is also invariant under the action of the group, but of course, as a vector in the Hilbert space, you might pick up a phase. Okay. So U of G acting on the pump state is the pump state up to a phase. And of course, because this is a representation, this here is also a representation. It's a one-dimensional representation of the group, which you might like to call a character or a homomorphism from the group into, if I write it this way, into the circle. Okay. And so the natural thing to say now is, oh, here is the charge, the G charge that can possibly accumulate there. It's exactly characterized by this little phase here. Okay. And so I will define the index of the loop as being that charge. And that charge, again, is a character of the group or is a homomorphism from the group into the circle. Okay. So I hope I've introduced the index now. Of course, this is, now you need to show that this is a good index, right? It's invariant of the deformations of the loops and so on. So here's the general statement. So the group has to be a compact group. I've defined the index of the loop, right? And so now let's see. So if I have a constant loop, hopefully the index is 0, right? So that's true. Now it's in a sense a complete classification. I can construct for any value, for any element, for any character, I can construct a loop with that particular. Oh, this should be a little h. Sorry, I changed notation. So, but I can construct a loop with that particular index. So it's loop index. And then the important things, it's the index is stable under deformations, right? So if I have two homotopic loops, then they necessarily have the same index. It's a complete classification in the sense that if I have two loops with the same base points, in fact, more generally with equivalent base points, then I can deform them with each other, into each other, right? So it's a complete classification. If you give me the index, I know exactly which class of loops I am in. And then the somehow necessary additivities of these indices, they're always of the same type. So if I stack two systems, and I make loops of these two systems, right? Then what is the pumped charge, which rather be the sum of the two pumped charges, right? So that's this first here, this first equality. And the second one is, if I make a loop, then let's say I just make the same loop again. Well, I better transport twice the charge, right? So it's additivity under concatenation. This is a symbol for doing the first psi, the loop psi1, and then psi2 is another loop that starts at the same base point. If I have that sort of, so I do two loops from the same base point, then the transported charge, G charge, is just a sum of the two charges. Okay, so again, these are all properties of what you would find in the good old Thouless pumping scheme. Although the group there would just do that. Okay, so I'm supposed to start at 10:02 or something like this, right?
Yeah, so we started 5 minutes late, or a little more than 5 minutes late. So yeah,
I'll
that's the shortly before 10 if you make it.
Yeah, I will. So I can give you. It's a very silly example, but here's a loop which gives me any index, right? Any charge. So it's completely artificial. But just to say, I think it's a good picture of what happens. So, so I pick one element of the home group here, right? So one of the, if you want to pick the charge I want to transport. So I will construct a Hilbert space, which is a three-dimensional, very silly Hilbert space. The basis is labeled by 0, h, and minus h. Right? It's a fine Hilbert space. The group action is just given by, it's, on any of, I define it on any of those by UG of, this is an element, this is a map from the group into S1, right? So I can evaluate H on G, right? This is how I define the action of the group. Fairly obvious that this is indeed a group action on that little Hilbert space. And then, okay, what do I do? You see, I start, so here's a representation. You can write this explicitly, but I think the picture is better. So you start with a chain where on each side you're in the state 0, right? If you think about it, there's no charge nowhere, right? Now, what you're going to do is you're going to create a pair of charge and charge at each pair of sides, right? But so I pair these, let's say the even sides here. So it's H minus H. You see, globally, I haven't created any charge, right? So that's during the first half of the loop, I do that. Then in the second half, I do the corresponding annihilation of two charges, right? But I do this not, I move by one side, if you wish. So now instead of pairing these two, I pair these two in the second half of the loop. Okay, on the whole chain, I just created two charges and annihilated them again. So nothing has happened. It's a very good loop. It's a G-invariant loop, right? But look what happens if I cut the Hamiltonian in the middle. Well, I create everything here, all the way here, right? That interaction here is not there because it cuts the cut line here. So then when I do the second half of the loop, I pair, to the left or to the right. So I pair those two, and this one is paired with a 0. Okay. So nothing happens to this one, right? It cannot be paired with its anti-charge, and it just remains there at the end. Okay. And so really exactly what this has happened, I've actually pumped a charge from -infinity all the way to here. And what am I left with? Well, exactly that charge labeled by H. Okay, so that's in fact this little picture, it's a proof of little point 2, I think, saying that for any element of the home group, I can find a loop that has that as its index. Okay. So maybe I will not. I'll go from here. So, like in all of these homotopic type of things, the basic thing you need to prove is you fix the base point, and you have a loop which has trivial index, so you should be able to contract that to a point. Once you're done with that, all the rest is fairly simple. And I will try to explain here a little bit even how that works with the simplest possible base point and your product base point. So it's a trivial base point. And I have a loop from that trivial base point to itself, and I want to contract it. Okay. So the idea is what? So you see, maybe the first thing you would like to do is, okay, I take the Hamiltonian, right? It's a Hamiltonian evolution. So I just put the label lambda in front of the Hamiltonian, and I send that to 0, right? You'd think, okay, at the end of the day, there's no evolution, so I will be back to doing nothing. Now, of course, this doesn't work because you need to have a homotopy of loops. So if you just send the Hamiltonian to 0, you'll start from a loop, but then when you change the Hamiltonian, you have no reason to end back on the initial state anymore, right? It's time-dependent situation. You will just end somewhere. And yes, at the very end, you would end back with a constant thing, but that's not what you're after. And you want to have a deformation of loops. So we're fighting against that. We want to deform Hamiltonians, but so that they keep generating, for all values of the deformation parameter, I still generate a loop. Okay. And of course, that needs to be done so that the range of the Hamiltonian stays finite. Right? You don't want to create long-range Hamiltonians and therefore long-range entanglement. So the way to do this will be in 3 steps. The first step is you take your loop and you want to split it in 2. So you want to find a new Hamiltonian which has no interaction across any cut. You pick a cut, let's say at side 0, and you create a Hamiltonian which looks the same as the initial one away from the cut, and still generates a loop. So really, it's going to be two separate loops, right? One on the left, one on the right, because you start on a product state. Okay. So now you have, in fact, two loops. So the problem remains a little bit the same, but the idea that you have only two half chains instead of one large chain. So what are you going to do for each half chain? Now you're going to do the same, and you're trying to cut this large loop into little loops on finite intervals. Okay. Once you've done that, then you're in a finite interval. So being in a finite interval is like being in, there's no long one-dimensional chain. Once you're in a finite interval, you can deform this very easily. Right? You don't need to be worried about any sort of locality anymore because you're just on a finite chain. Okay. So that's the idea. You split into two, then you split into little intervals, not too large, but large enough. And of course, you cannot do that exactly, right? You will make an error. So you'll have, your thing with small intervals is going to generate almost a loop. So you'll still have a little bit of an error. So you'll still have an error, which means a Hamiltonian with a small interaction, weak interaction, right? You have a small loop. So at the end of the day, you need to contract that. You contract each of these single interval loops, and then you need to contract a short loop. It's short, but it still lives on the whole infinite chain. So still a bit of tricky thing, but that's the idea. Yes,
So, is it like totalization or
totalization?
Trotterization.
Trotterization. Huh, interesting. So technically, not at all. I think no, it's not related for the same reason. If you just trotterize, so you will indeed get the Hamiltonian is generated by a sum of local things that commute and so on. But by the same reason, if you take only part of them, you will not generate a loop. So you will keep locality by doing this, but you will lose the notion of a loop. So that's exactly the problem, right? So you see, I won't go into these words here. But so let's just think of the first step, splitting a loop across one edge. Okay. So you remember, let's go back to the picture. The picture is probably the easiest thing to understand. I have the pump state is this thing. So it differs from the initial state only close to the cut, right? So because of that, you can, in order to get there, I use the Hamiltonian which lives on the whole half-Indian chain. But afterwards, because out there the state is the same as the initial state, in fact, I could have done that just as well by acting only locally here close to the cut. Okay? So that I can always do. Now, can I do that in a G-invariant way? That's the question. Well, if there is a non-trivial charge here, then no, because that would mean I could get rid of the charge in a local way. That I can do. But if I start with if I have a loop of which I assume that it has trivial index, then no charge has actually been accumulated there, I will be able to do that. So I will be able to, instead of acting on the whole half-infinite change to get this state, I will be able to find another generator, which acts only locally here and does the same thing. Okay, and I can do that by just acting on that left half chain. And so this is really the whole point. The other way of saying this is I can, so where is it? Yes. I can modify, so I can start with a full Hamiltonian. I have one part just on the left, the other one just on the right, and something in the middle, right? So what I can do is, if I were to ignore what is in the middle, I have always a product, but it's not a loop anymore. But now by acting only somewhere in the middle, I can change that and get back to a loop. Okay. And so, you can do that only if you have a vanishing index, and the result, which is here, just look at these three last lines here. I can take my original generating, my Hamiltonian K generating the loop, modify it only locally in a G-invariant way because the index is trivial. And I have reconstructed a loop. Okay. And this is done in such a way that the original Hamiltonian plus that change is actually split. So it acts only on the left and on the right, but there's no interaction across the grid. So that's what I wanted to do. By modifying the Hamiltonian, I have now I have split the whole loop. Throughout the evolution, the left doesn't talk to the right. Okay. And then, okay, you know, let me not go into more. So again, what you do when you want to do that here at 0, but also at minus r and also at plus r. Now, of course, if you do it here at 0 and then at minus r, there's always tails in this thing, right? When I say that Hamiltonian E0 is localized around 0, yes, it's mostly there, but with kind of exponential tails that go out. So if I split here and then I split there, I will mess up a little bit the splitting here. Right, so but still I do it, and what I actually need to do is I do that splitting along, you know, these intervals j. In order to correct for the mistakes, I have to in each of them split again somehow. So I do another round of splitting and I move by a half interval, and I managed to do this. So I have this, you know, I have a split interaction on the j's, a split interaction on the i's, and there's still a little bit of an error. But the point is, you know, if I were to look only at that first part, it's totally split in these long intervals and it generates a loop. The same to this one. And then this is a loop, so this will also generate a loop, and this has small norm, this very small interaction. Once I'm done with that, it's a question of contracting these things, but I don't need to worry too much anymore about locality because I'm in finite intervals. And so I'm good, I can do that. I can contract all of these loops. And well, you know, that's part of the central argument, right? If the charge was trivial, if the index is 0, then the loop is contractible. And from there, I can do all of this. So before stopping, I just want to say a few more words about, you know, the relation of all of this to the classification of SPT phases and so on. And this was a one-dimensional system. So before somebody asks, so what about higher dimensions? I will answer that question right away. So in D dimension, so, you know, what was the game? The game is I'm in one dimension, I pump charge, and then the pumped state is really a modification of the initial state locally around the cut. So I've lost one dimension. If I do that in high dimension, here's the thing, I do that in 2 dimensions, I will pump things from infinity. The new state will differ from, you know, the pump state will differ from the initial state along that vertical line, right? So effectively, the pump state will be a one-dimensional state out of a 2-dimensional situation. If I were in D dimensions, the pump state would be a D-1 dimensional state. And what sort of state is it? It's still a short-range entangled state, and it's still, you know, now along that direction, and it's still a G-invariant state. So what you have is really, if you're bumping charges in D dimensions, the pump state is a D-1 dimensional SPT state. Okay, and so for us it was 1 to 0. How do you classify 0-dimensional SPT states? Well, by representation theory. So what do you expect is, well, if you're in 2 dimensions, you're pumping charge, the loops should be classified by the D-1 dimensional index of SPT states. So in 2 dimensions, you should get H2, the classification of the 1-dimensional SPT states. In 1 dimension, I got, you know, the homotopy group is exactly the first cohomology group. So it's the classification of the 0-dimensional SPT states. So that you expect that to work in high dimensions as well. And at least, you know, there's one thing which is true probably in all dimensions. The classification of loops in D dimension is given by the classification of states in D-1 dimensions. Now, okay, you can ask, what is the classification of states in D-1 dimensions? Well, for small dimensions is the cohomological classification. In high dimensions, probably not anymore. So that I don't know. But what we did here is really we constructed explicitly the index, right? You could have a slightly weaker aim to say, just show that, you know, classifying loops in D dimension is just the same as classifying states in D-1 dimension without necessarily knowing what is the classification in D-1. And of course, you see, that's the technical challenge is here we have this very nice tool that we could represent everything in the same Hilbert space, and then we can do our game in one Hilbert space. In high dimensions, it's not the case anymore because this state, you know, it's still an infinitely extended state. So the pumped state and the other one are still different also at infinity. Only out here at infinity, not there, but that's sufficient to be a problem. So technically, the whole strategy we use that just doesn't work in high dimensions. So the fundamental idea should still hold. I think I'll stop here. Thanks.
Yeah, so I have a question. So why aren't you happy with an MPS classification? Also, like together beginning
right. So there's two things at the beginning. So the MPS classification, so it's of the states, right? Not of loops. Yeah. I'm not, maybe there were these ideas were around in the physics. I don't exactly know how far at the end and probably use MPS classification now. You see, it's always the thing, right? You will tell me, well, MPS, you can approximate the state in one dimension with an MPS. But, it's always then a question, okay, but as you do the approximation, when you actually lose, for example, the necessary locality of the generators. Okay, so morally I agree with you that MPS classification should be sufficient. Now, both technically, I'm not sure whether it could actually make it work. And also fundamentally, like, okay, why, there's no reason why you need to use MPS representation for state. It's maybe a convenient trick. You don't necessarily need it. Okay. And so, that's why you can do it without referring to matrix product states. I think I just refer this. Yeah.
Yeah, so I guess your approach here agrees with what you might get from intuition of applying this unit formula whenever I just consider one-dimensional SPTs classified by some symmetry group, but then I also had a time translational symmetry.
Yes, exactly. So I think this idea exists to the classification of Roeck.
Yeah.
Because it is a Roeck SPT phase, right? The time dimension group. So yes, I think exactly. If you look there, people have, that I wrote here. I think this is probably the formula you have in mind. Yes, I think all of this. If you allow yourself not to go into too many technical details, but think just in terms of okay, I can do this scope, you will be able to. We would have guessed this absolutely. There's no question about that.
In the top of GNS presentation, you mentioned that when we actually do the orbiter on cosine -1, the result is still cosine -1, but up to an overall field. Can you say a bit more on why we got the field?
Oh, so what was that? This here, right? So it's the next slide. So let's maybe start with this one. So that is the state out of which I construct the GNS chromatograph, the omega 0. It is by assumption the G-invariant state. That's the assumption. I have a representation of the group on that vector state now. If it is invariant into G, it's invariant into the action of the group, you expect in fact that state must be invariant of the U. So a phase has this has to be an eigenstate of the unit path. Right? Disagree with that? Or you? So forget the GNS representation. If I tell you, look, you have a state in a Hilbert space.
Yeah.
You have a unitary, and your state is invariant underneath the action of that unitary. What does that mean? That means when you act on the state, you get the state itself.
Yeah, but the phase that is what?
No, the state can be anything. The phase can be anything because the physical state is independent from the phase.
Okay, so so on the right hand side of the equation, the phase that is what?
Yes. So that's because good one. So I could have done two things here. I could have said put the phase here, right? And then the index would have been the difference between this age and that age. So it's really, the fact we actually have to use right? but I can also redefine the U, U of G. I can look at the phase I get here, take it into the U of G, and then I have an actual zero phase. And for simplicity of the presentation. Okay. So there was, I don't know.
There's a question on the chat.
Okay.
You can quickly read it. When you are splitting these loops, are you assuming no interaction between the left and the right side?
So when I split the loops, I start with a loop which has interaction between each, right? So that maybe just go back to where I do this. Right, so here it is. So so I start with a homology which has a purely left part, a purely right part, and well, all the interactions across the right? So my goal is to change that locally. So you see, if I just get rid of the K0 here, the interaction across the cut, well, that gives me a good evolution, but this is not the loop anymore. Okay. So what I'm trying to do here is to, in a sense, replace this K0, this interaction before the cut, by something which is still locally localizable in the cut. There is interaction between the left and the right. If you just look at that. But so that overall, so the new guy, which after I write K plus this E0, I make a modification of the full interacting Hamiltonian locally, so that now it's really split, so there is no interaction between left and right, but I still generate the loop. Okay, so along the loop, I'm always going to have a state which the left cancels out. Okay, and I can do that. That's the claim. I can do that, and it's not completely obvious.
Good, thank you very much. I think, yeah, let's thank Sven again.